All right, folks, today we're going to look at Taylor polynomials. So what kind of functions can you approximate with polynomials? And this is where this unit actually gets really interesting, and we get to the application and to some pretty cool math that shows up from this. So what are Taylor polynomials? So a Taylor polynomial is a polynomial approximation of another function that we're going to call f of x. And so this is what's really cool is Taylor polynomials will approximate any function by kind of looking at the behavior of that function and then writing a polynomial. And remember, a polynomial is something where you have an x squared term, an x cubed term, an x to the fourth, some number of functions. So we can take something like sine of x and write an approximation that's going to be something like, 5x cubed plus 3x squared minus x. That's obviously not the approximation, because if you graph this and sine, you see that they look different. But if you have sufficiently complex polynomials involved, you do end up getting kind of perfectly the perfect sine graph. So they're generated using the following expression. And so the expression for a Taylor polynomial is that the term a sub n is equal to the function, the nth derivative of that function, at some point a divided by n factorial, and then times x minus a to the n. So the nth term in the polynomial is the nth derivative at a divided by n factorial times x minus a to the n power. So if we wanted the fifth term, you'd replace all these n's with 5s and so on and so forth. So let's look at an example of this. Right, the third degree Taylor polynomial for the function f of x equals ln of x centered at x equals 1. So this centered word right here is that a value that we had before. So if we go back, this right here, this a, is the center of the polynomial. So it's basically the value that we're approximating around. And this is something that I think is easier to kind of show in person. So at some point, we'll probably do something as a class, but if you want to kind of go through it a bit more together sooner, talk to me and I'll kind of walk through the logic of what does this center actually mean. Okay, so coming back to our example, we're centered at x equals 1. And so we're going to write out our terms. So first we're going to write the 0th. So we always start with Taylor polynomials, we always start with the 0th term. And so we plug in n equals 0. So that will be the 0th derivative of f of x. So that will just be f, no derivative. F of 1 divided by 0 factorial times x minus 1 to the 0th power. And that will equal just f of 1, because 0 factorial is 1, x minus 1 to the 0 is 1. So this ends up giving us just ln of 1. And our first term will be the first derivative of the function at 1 divided by 1 factorial times x minus 1 to the first power. And f prime of 1 is, well, let's write those off to the side here. F prime of x is equal to 1 over x. F double prime of x is equal to negative 1 over x squared. The third derivative of x is 2 over x cubed, and so on and so forth. You can continue that, but I just wanted to write that off to the side. So the first derivative at 1 will be just negative 1, divided by 1 factorial, which is also 1, times x minus 1. So that first term there is x minus 1. And then our second term, so remember we've gone 0, first, second. So second will be the second derivative at 1 divided by 2 factorial times x minus 2 to the second, sorry, x minus 1 to the second. And that will give f double prime of 1 is negative 1 over x squared. Sorry, this should have been plus 1, right? Let me check my notes. Yeah, plus 1. That was my bad. This will be negative 1 over 2 factorial, which is just 2. So I'll write that, times x minus 1 squared. So that will give us negative 1/2 x minus 1 squared. So these are our first three terms. We basically have ln of 1 plus x minus 1 plus negative 1/2 x minus 1 squared. So again, our 0th term, our first term, and our second term. So this right here is approximately ln of x. If you graphed this, you would see that it's not great, but it's, it's reasonably close to this. Oh, wait, we have a problem here because ln of 1 is 0. So we actually do need to write our third term to get the first three non-zero terms. So f triple prime of 1 over 3 factorial times x minus 1 squared is 2 over 3 factorial, so that should just be 1 over 3 times x minus 1 cubed, which is 1/3 x minus 1 cubed. And so this here is our third term. So these right here are our first three terms. Not because they're numbered 1, 2, and 3, but because of the first three. Sorry, this didn't even ask for non-zero terms. Third degree means go up to the 3. I'm mixing this up with a later sample problem. Sorry for that confusion, but that's the idea. If you plot all this out, you'll see that you get something that starts to look like a natural log. If you continued this pattern and wrote more and more terms, you'd see something that looks closer and closer to ln of x. So then the question is, how is this an approximation? So this seeks to match the curvature behavior of a function by matching the derivatives. So in other words, if we imagine just a real basic sine curve, so let me sketch this like that. And I'm going to do this real rough, but you'll be able to hopefully get the idea. So let's pick yellow. So a 0th order Taylor polynomial, if we want to pick this point as my center, 0th order would just be a solid line to approximate it, because it's just, some constant. That's not a very good approximation. But if I match the slope here, then, I might get a slightly better approximation because it'll match with the slope for longer. If I try to put a quadratic here and I match the second order behavior, then, I might get even more accurate. If I try to match third order behavior, you see I get that. Now let's switch to another color. Let's go blue. If I try to match fourth order, I might end up getting something similar to this. And so you can kind of see how if I have increasingly complex polynomials, I can get more and more of this behavior accounted for. Now this is a very hand-wavy explanation. On the site, I'll link to a calculator demo that will kind of show you can actually increase the order and see actual calculations for yourself. But this is the idea. If we go to higher and higher orders, we get more and more of that behavior incorporated. So for example, if we have x minus 1 to the 5th, well, that means we've got a 5th order polynomial. We can have, 5 of those bumps to kind of match up. And so ultimately, the more terms you have, the more accurate. And therefore, by extension, infinite terms equals exact match. So what this kind of means as an interesting side note is literally any function can be written as an infinite, well, any continuous function, anything that you can write f of x, can be written as an infinite series as a polynomial. And so polynomials are a lot nicer to work with, and that means we can write any function as a polynomial and do some easier math. So this is ultimately what we're culminating with, is the idea of being able to approximate or write a very specific polynomial as an approximation of a function.